I'll put the notes up on the screen. Okay, so can you see the notes? Okay, so morning, Stephen. Stephen's joined us.
Hi.
We're just getting started now, Stephen. So welcome.
Good, thanks.
Today is more or less a summary of things we've already talked about before. We've looked at the most common types of air conditioning systems that we deal with and some of the fundamentals of those systems. So when we commence a new project, a decision has to be made on what type of system is most appropriate for the project. And the decision-making process will include the client, who may have preferences for particular types of air conditioning systems, and he may have preferences for different manufacturers, he or she, or they. They might have their favourites that they like to use. So all that needs to be talked about and considered. And importantly, budget constraints are always an issue in this process. Our role in the process, Anand is joining us. Our role in the process is to advise the client on the relative merits of the different system types and present options or make recommendations for their consideration. Morning, Anand.
Morning, everyone.
We've just started going through the notes.
Right. Okay.
So in the selection criteria, at least the following criteria will be considered: the type and the size of the project. That will determine the appropriate equipment. The estimated air conditioning system cooling capacity. If you haven't done the loads already, you can make an estimate of that using the ERA check figures. Spatial requirements or available space. So the building design will probably be done, or it might be an existing building, and there may be only a certain amount of space available. So we're going to have to work within that. Energy efficiency or power requirements, or again, what power is available. If it's an existing building, there might be only so much power available, and we have to work within those constraints. Acoustic issues, need to consider the building occupants and adjacent properties. So equipment makes noise. We need to be aware of that and take that into consideration. What are the access and maintenance requirements? And the cost, obviously, capital and operating cost. The cheapest system will most likely be the most inefficient energy-wise. So it will cost more to run, but it might be cheaper to buy. So again, the client will have to advise you on which way they want to go with that. Types of air conditioning systems and typical applications. So these, we've talked about these before, but there's a little bit more detail now and things to consider. These are the most commonly encountered systems and some typical applications. The list is set out in ascending order of capital cost in general terms, depending on the project complexity. So from 1 to 9, 1 is the cheapest, 9 is going to be the most expensive. In between, it depends on the size of the job and the type of job as to which one you would choose. So firstly, the DX split, air-cooled, non-ducted. So we're looking at wall-mounted fan coil units, ceiling cassette units, that type of thing. Each one paired up with an individual outdoor condensing unit. So houses, apartments, equipment rooms. Typically, equipment rooms might be a comms room. Schools, schoolroom, classrooms, and small offices. But don't forget outside air. So if you haven't got natural ventilation, you need to bring in some outside air for these systems. Number 2, DX split ducted system, air cooled. You can get up to about 95 kilowatts a system with these. I think Temperzone goes up to about that capacity. With the Japanese models, there's smaller capacities for individual systems, probably about 25 kilowatts. Again, houses, apartments, schools, offices, shops, public areas, small runs of duct typically. In that case, you can duct the outside air. Thirdly, packaged air conditioning units, air cooled, ducted supply and return, and you can get up to about 200 kilowatts per package unit. Normally they're installed on the ground or on the roof. Typically low-rise offices, large single-level shops, say a shopping centre or a big box shop like a bulky goods store, factories, warehouses, public areas. And be aware that there's some external ductwork and some building penetrations. So you're going to penetrate the roof or walls of a building to get the ductwork in and out of the building. And this puts a bit of a limitation on the height of a building that you can serve, because if you're going to put package units on the top of a building with several stories, then you need risers for the ductwork, and that can be significant space. Fourth, VRF. See if I can highlight that. VRF heat pump, air cooled, ducted and non-ducted fan coil units. So again, if we have a look at a schematic, can you see that schematic? So you can have a range of fan coil unit types here, as you know, ceiling cassettes, wall-mounted units, ducted units, etc. Notes. Typically large houses where you don't need to have, we'll go through it in more detail in a minute. Large houses, apartment buildings, schools, offices, shops, hotels, small hospitals, public areas. So fairly broad use, but obviously at 150 kilowatts per system, as the building gets bigger, you need more systems, more space for condensing units, more space for risers for pipe work, and so on. VRF heat recovery, air cooled, ducted and non-ducted fan coil units, same sort of system, up to about 125 kilowatts per system in this case. So in the same types of applications, but I've left out large houses because typically you wouldn't use a heat recovery system on a house, because you don't normally do that, but I mean, you can, but it's an added expense for something that's probably not really necessary. Number 6, and be aware that, I mean, these are not the only systems available, but they're the ones that we most typically come across. Packaged air conditioning units, water cooled this time and ducted, up to about 45 kilowatts per package unit, connected to a cooling tower or fluid cooler, so you can have any number of these units. Typically used for apartments, schools, offices, shops, hotels, public areas. Number 7, we've got back to VRF again, water cooled this time, ducted and non-ducted, but only up to about 100 kilowatts per system. So if you've got a big job, you're going to have a lot of condensers. VRF heat recovery, water cooled. So again, same sort of thing, but heat recovery this time, same sort of applications. When we get into the chillers and boilers, so now an air-cooled chiller, the chilled water is used for cooling, and you can get up to about 1,500 kilowatts per chiller. I don't think you'll find a chiller bigger than 1500 kilowatts, and they get extremely big in physical size. A 1500 kilowatt chiller is about 15 meters long. So you need a lot of space. And if you're going to put it on a roof, you need a lot of roof space.
Sorry, Peter.
And
Can I
yep,
actually ask? I've got a mental blank. So number 7 and 8, what's actually going
Yep.
on with those VRF water cooled systems? So is it the condenser that's water cooled?
oh yes, yeah.
Okay, so
Yes, so when I say air cooled for 4 and 5, air cooled means it's an air cooled condenser,
mhm,
and 7 and 8 is a water cooled condenser. That's right. So,
mhm.
and I'll talk a bit more about this, but with a water cooled condenser, you can have these inside the building. An air cooled condenser must be outside.
Yes, yeah, I have seen them before. Yep, yep,
Yeah, okay. And so they have some benefits because they take up less space.
yep.
When you've got air and less pipe work involved. So you can have
Yes, yeah.
you can have the condensers on the level served.
And just have
The
one
refrigerant
condenser riser going up and down the building to each level, yeah.
condenser water, yeah.
Condenser water riser, yes.
Yeah. So I'll talk about that in a minute. I'm just sort of talking about the options, I guess, at the moment, but that's a good question. But feel free to jump in any time if you've got a question. That's fine.
Thanks.
So air-cooled chiller, got to be outside. Okay, it's air-cooled. We'll go through it in a bit more detail. I've got some pictures to show you as well, just to make it a bit clearer. And this would be coupled with, so that's 2 water for cooling, coupled with a boiler, a hot water boiler, which might be a conventional hot water boiler. They can go up to about 5,000 kilowatts each, or a condensing hot water boiler, which we talked about in previous sessions, but only up to about 1,200 kilowatts per boiler, as far as I'm aware. So virtually any project can be served with this sort of equipment. The limitations on air-cooled chillers obviously are the space required. So I've made a list there of a few projects: high-rise offices, shopping centres, laboratories, hotels, universities, campuses, you name it, you can probably do it with this type of system. Central energy plant may be an option, but again, limited by the size of the chillers. And then finally, a chiller, a water-cooled chiller. So again, it's a water-cooled condenser for the chiller. Needs a cooling tower or fluid cooler, or several of them. But you can get capacities for cooling of up to about 10,000 kilowatts per chiller. Now that's pretty big. Very rarely use a chiller of that size, but that's the range you can go up to. I mean, you can get very small chillers, but you can get the full range right through to 10,000 kilowatts. And again, that would be in addition to a conventional or a condensing boiler for heating, if you need heating, which I'm sure you would in Victoria. So I'll move on to consideration of selection criteria. The following information relates to some of the important criteria to consider when selecting the type of air conditioning system to use for a project. The criteria include spatial requirements, energy efficiency, acoustics, installation, maintenance and costs. Again, it's in ascending order of capital cost in rough terms, depending on the size of the project and how complex it is. And the type and size of the project and the budget allowance is obviously fundamental to this process. So firstly, let's have a look at the DX split systems. And I'll put some pictures up just to remind you. So wall-mounted fan coil units. Okay, we've all seen plenty of those. And a condensing unit. Okay, I'll just so one indoor unit for each outdoor unit. Be aware of the allowable length of refrigerant pipe. These sort of systems are limited to maybe 20 metres, perhaps up to 30. So you've got to have those units fairly close together. If you can do them back to back, inside and outside, that's the most economical way to do it. Each system can be controlled independently. Condensing units can cause noise issues, so beware of where you locate them. And excuse me, clear space is required for satisfactory condenser operation and maintenance. So I'll just have a look at that condensing unit again. So air has to come in to the condenser and be discharged from the condenser at the front. And these come in various sizes and shapes. They might have 2 fans, so they're a bit taller, a bit wider. But you need to have a look at the manufacturer's recommendations and make sure that you've got intake and outlet space around them. Otherwise, they won't work properly. Sometimes an architect will try and get you to hide these condensers, and that can be a bit of a problem for them to work properly. If they want you to put a condenser inside an enclosure, you need to make sure that it's well ventilated. You've got louvers all around it so that you can get the air in and out. Sometimes they'll want you to put them in a plant room. That can be quite tricky. It can be done. Just make sure you've got good space for intake and exhaust and discharge of the condenser air. Minimal maintenance is required. The condensers need cleaning out every 6 months or 12 months. Give them a hose to clean them if it's in a dusty environment, and simple controls. And just a question there, is outside air required? And that'll have to be dealt with. If you're in a space that hasn't got natural ventilation, you'll need to provide some mechanical ventilation. Okay, the next one, the ducted split. Considerations are basically the same as a non-ducted system, except that you're going to have filters in this case. So, so here's some ducted units. These are the Mitsubishi range, which I happen to have on file. So this is the return air inlet on this unit. That will have a box on the back or a plenum with filters in it. So you need access for to take the filters out and replace them or clean them. But you also need access to the electrical components of the unit and the pipework connections here. So just bear that in mind with a split ducted system. And again, excuse me. Again, you've got the same issues with the external condensing unit. And typically it's one condensing unit to each fan coil unit. Moving on to packaged air conditioning unit, air-cooled with ducted supply and return air. Okay, the package units are installed outside. So a roof platform may be required if you have a number of units, or even one unit. The roof may not be strong enough to carry the unit, so you might need a platform. And you'll need roof access if it's on the roof. They may be installed on the ground if there's sufficient space and if the building allows for it. But if you've got a bulky goods store, like let's say a Bunnings, they're not going to be on the ground. They'll be on the roof. So you've got to be able to get to them. You've got to have safe access. So you probably need a walkway on the roof, and the unit will probably be on a platform. There'll be several units. They'll be on platforms because the roof is not designed to carry a unit. So I'll show you a picture of typical air-cooled package unit. It's not a very good diagram, but you can see there's a supply air connection there, return air connection. Again, you have a filter box on there with filters in it, and the condenser on the top. You need clear space around the unit for condenser air to come in. and clear space above to discharge the hot condenser air, and also maintenance. Economy cycle may be required by NCC Section J, so you need to look at that. That depends on the location of the project and the capacity of the system, the airflow. And that'll provide some improvement in energy efficiency, but it's an expensive thing to do, so it's really a Section J requirement if it's needed. You need filter access, and the controls are relatively simple, unless I mean, you can make it more complicated if you want to put in a DDC or BMS system to control the whole site, but individually they can be quite simple controls. Mention here again building penetrations for ductwork, so be aware of that. If it's a single story bulky goods like a Bunnings, relatively simple to come through the roof and back out for the return air. But if you've got more than one story, you need a riser for the ducts. Now I'll move on to VRF heat pump, air-cooled condenser. So I've got a picture of those, I will show you. And I mean, you've all had experience with these units already. So you're pretty much aware of what they look like, but this is actually heat recovery units, but air cooled. So you can see the condenser. It's not a very good picture, but can you see it all right? You've got a fan on the top, condenser fan. You've got condenser around the sides. So again, you need clear space for the air to come in and out of the condenser, and for maintenance access. You can have one or more outdoor units for multiple indoor units. So you can build the capacity. Each system, as I said before, is, I think for air-cooled with 150 kilowatts. So if you need more than that, you can keep building systems, but you'll have a lot of condensers. So if you look at, again, this is heat recovery, but for the heat pump, the capacity goes up to about 150 kilowatts. So if you've got a 1,000 kilowatt job, you're going to have 9 or 10 banks of condensers, and each of those 150 will be at least two condensers. So you're going to have maybe 20 condensers for a 1,000 kilowatt project. So they're the sort of things to consider, whether you've got sufficient space to do that and whether that's an economical way to do it. You need to be aware of the allowable refrigerant piping lengths between system components. You've got a bit more flexibility here than you do with just a single split, but you still do have restrictions. So you need to look at the manufacturer's details to find out what you can do with the pipe work. They might say that you can have a kilometre of pipe, but that's not before you get to the first unit. That's in total for the whole system. So you need to study that and understand what that really means. There's a limitation between the condenser and the first unit, and then from the first unit to the second, and so on. So have a look at that. And each manufacturer will have slightly different requirements. With a heat pump, you need to be aware that only one mode can operate at one time. So it's either heating or cooling. You can't have both at the same time. So you need to group the fan coil units in similar thermal zones to ensure satisfactory operation. So if you've got some small offices along a perimeter wall, they can operate together. But if you have a meeting room on the same side, it's probably not a good idea to put the meeting room with the offices, because that's a transitional area. And if they come in and take control of the air conditioning, that's going to affect the offices, or vice versa. So just be aware of things like that. The condensers are most likely going to be on the roof. They might be on the ground, but usually they're on the roof. So you might need a platform, and access will be required, safe access. For large projects or medium rise height projects, the condenser plant space can be significant and difficult to achieve. So that's a very important consideration. The individual fan coil units can be controlled independently, and variable speed compressors in the condensing units can accurately meet the loads. So there's potential energy savings there. These are very clever systems, but they have their limitations. You need to be aware of the occupied space refrigerant concentration in the event of leakage and mitigate that where necessary. So I think you would have all come across this issue where if you have a leak in the system, you need to look at all the spaces that are served by the air conditioning system and consider the potential concentration and deal with that. Condensing units can cause noise issues, so be aware of where they're located and their surroundings. And again, the same things, clear space required for condenser operation, filter maintenance, and so on. And also, if you've got a multi-storey building, the space required for the refrigerant pipe risers can be significant. And if you've done a job with more than one story, I'm sure you've come across this issue where you can have a lot of pipes that have to go between floors, and you need the riser space. So be aware of that and make sure that that can be provided. So now VRF heat recovery air-cooled condensers. So similar, again, condensers outside the building, similar considerations to the heat pump system, but in this case, cooling and heating can operate simultaneously with one system. So that improves the energy efficiency, but increases the cost. They're more expensive, and the total capacity is a bit less than the heat pump system. It's beneficial to group different thermal zones on one system to take advantage of the heat recovery. This is what you're trying to do. So if you've got an east zone and a west zone, you can combine those, or with the centre zone, everything can be combined, basically. And you'll get energy efficiency because the heat extracted from one zone can be put into another zone, if that's how it's working. So east zone in the morning might want cooling, whereas the west zone might need heating because it's cold outside, but you've got sun on the eastern windows, so that zone is warming up, but the west zone is still cold, and the reverse will occur in the afternoon, perhaps. So there's benefits there in energy efficiency. And you'll need ceiling space and access for the branch connection boxes for the heat recovery system. Now, packaged air conditioning units, water cooled. Any questions so far? If you just want to have a... All good? Okay, I'll just show you a water cooled package unit. Again, it's not a very good picture. Can you see that, Hudson? Nod of the head. Thank you. So in this case, this has got a water cooled condenser. It's inside this unit. It's got a what they call a tube-in-tube condenser. So you've got refrigerant and water in the tubes. It's the heat exchanger inside. These two pipe stubs here are for condenser water. And this is obviously the supply air duct connection, and the return is on the back. So these are quite useful. Firstly, you're going to need significant space and access for cooling towers or fluid coolers for heat rejection, and together with pumps, condenser water pipework, valves, and possibly heat exchangers. So significant maintenance required and space. So if I show you a picture of a cooling tower, sorry. Right. that's a large system, but depending on the size of the project, you can have a lot of space required for cooling towers. So be aware of that. You'll need chemical treatment for the condenser water system. Many indoor units can be served by a central heat rejection plant. So it's almost unlimited, really, how many indoor units you can have. These units are installed indoors in a ceiling space or in a plant area. So there's really not much limitation on how many units you can have. The energy efficiency is improves because they're water cooled. We've talked about that before. There's basically no restriction on condenser water pipe lengths because the refrigerant pipe is packaged inside the packaged unit. So you don't have to run any refrigerant pipes anywhere. You've just got to run condenser water from the cooling tower to these units. Each packaged unit can be controlled independently. They're installed within or adjacent to the occupied space served, so minimal ductwork is required. However, the package units have a compressor in them as well, so that can cause noise issues. So sometimes acoustic treatment may be required in the ductwork, in the return air and the supply air ductwork to take out the noise of the compressors. You can also get jackets for the compressors, which will help to absorb some of that noise. So just be aware of that. If you're going to put one of these units in a ceiling above an occupied space, there's a good chance that it might be a bit noisy. And I have seen them used in hotels. We did a job in Sydney where we had to take them all out because they were just too noisy. We didn't do the job originally. We replaced them with chilled water units, but it was quite a big job. It was probably a couple of hundred rooms, which all had water-cooled package units, and they were noisy. A hotel room, typically you need to achieve about 30 to 35 dBA, and the package units were causing 45 dBA in a hotel room, which has just got a bed and a bathroom. Too noisy. So, and you need filter access and access for the package unit, which will be above the ceiling or could be in a cupboard. Okay, now we come to VRF heat pumps, water-cooled condensers, ducted and non-ducted fan coil units. In this case, condensers are inside the building, usually in a cupboard, or there might be a plant area, but quite often the architect will provide a cupboard in the corridor next to a switchboard or something that you can put them in, and it's quite convenient. The refrigerant pipework is the same as the air-cooled systems, but for the heat rejection, you've got condenser water. So, so again, we're going to have cooling towers or fluid coolers for heat rejection, together with pumps, condenser water pipework, valves, and possibly heat exchangers. So significant maintenance required, chemical treatment required for the condenser water system. I mention heat exchangers here because I know some manufacturers won't allow condenser water from a cooling tower to go through their condensers. It may have changed, but I know that Daikin used to, and probably some others, don't want that to happen because the cooling towers pick up dirt. The water can pick up particulates which are circulated through the system, and they can block up condensers. So Daikin will always request, and it'll be in their manuals, you'll find it there, that they require a heat exchanger to separate the water-cooled condenser from the cooling tower circuit. If you've got a fluid cooler, it doesn't matter because that's a closed system. But for an open system, you might need a heat exchanger. Mitsubishi weren't phased by that. They didn't require a heat exchanger, but you'd need to check their latest requirements because if you've got a heat exchanger, you've got more pumps, and valves and pipe work and more cost. With the water-cooled system, the energy efficiency is improved. Again, here there's essentially no restrictions on condenser water pipe lengths. So that's a big advantage. You don't have to worry about condensers being outside the building. They're going to be inside. Your condenser water pipe can run virtually unlimited lengths. And the condensers are located close to the fan coil units, so there's not a lot of refrigerant pipe involved. And you have one or more condensing units for multiple indoor units. Same thing. And I've talked about the enclosures, and the refrigerant is the same as it would be for air-cooled. So there's quite a number of advantages with water-cooled, but there's with the heat rejection plant, there's a fair bit of cost involved in that. As I've said earlier, for the air-cooled systems, you need to be aware of the allowable refrigerant lengths. With a heat pump, in this case, you can only have one mode, and so on. That's the same as the air-cooled systems. And I've just got another note there about the heat exchangers, so be aware of that. Keep that in your mind when you're looking at a system. Maybe these notes would be helpful for you when you're considering what sort of system to use and the things to look out for. But this is not an exhaustive list. There will be other things, but these are probably the main points. So the next one is a heat recovery VRF, water-cooled condensers with ducted and non-ducted fan coil units. Again, condensers inside the building in a cupboard or a plant room. Considerations are basically the same as the heat pump VRF. Again, with the same exceptions I talked about before. So you can have cooling and heating operating simultaneously. Group the different thermal zones, and it works. That's the way to do it. Works most efficiently, and the ceiling space is required for access to the. Access is required to get to the branch connection boxes. Okay. Now we'll look at chillers and boilers. Air-cooled chiller. So the chiller is outside the building. It's got an air-cooled condenser. It's got to be out in the weather. The capacity is limited to around 1,500 kilowatts per chiller. The physical size increases with increasing capacity. If you look at a chiller, an air-cooled chiller, you can usually work out roughly how big they're going to be if you haven't got the catalogue with you by the number of fans on the chiller. I'm not going to quote the capacity per fan, but maybe around 100 kilowatts per fan. So with the 1,500 kilowatts, you're going to have probably 16 fans or something. They're big machines, and if you've got more than 1,500 kilowatts, you need multiple chillers. So they take up a lot of space. Compressor options include scroll compressors, magnetic bearing centrifugal, or helical rotary, or called screw. Each one has different energy efficiency, so you need to look at that. Consider how many capacity steps are required. You might have multiple. If it's a scroll chiller, usually you'll have multiple compressors which are on or off. So that will give you capacity steps. If you have 4 compressors, you've got 4 steps of capacity. But some compressors, like a scroll or a centrifugal compressor, is available with a VSD. A magnetic bearing centrifugal chiller compressor may come with a VSD integral with the compressor, but just check that it has got that. But for a screw compressor, you'd need to pay extra money for a VSD. and that's available to increase the energy efficiency. So I'll just put up an air-cooled chiller. So you can see the fans, condenser fans on the top, condenser coil. You need clear space around that for the air to come in and discharge. And underneath you've got the evaporator where the chilled water is produced, and the compressor. This compressor looks like it might be a screw compressor, but as I said, you can get magnetic bearing centrifugals, which are the most efficient, but also the most costly. So you just got to weigh all these things up and decide which way you want to go, or which way the client wants to go for energy efficiency versus cost. So if the chiller is on the roof, you'll need, well, if it's a concrete roof, the chiller can go on the concrete, but if it's going onto a metal roof, you'll need a platform and access, as you do for the external condensers. Space and access is required for the chillers, together with pumps, chill water pipework, valves, etc. The chillers could be on the roof or outside at ground level or podium level. Significant maintenance is required. Now these 2 points, in a chilled water system, same as we discussed previously, it's likely that you'll need an automatic bypass valve to maintain the required minimum flow. So each chiller will have a minimum required flow. Sometimes that might be the same as the design flow. In other words, you can't reduce it, but a lot of chillers nowadays, because of energy efficiency requirements, will allow you to reduce the flow through the chiller, but to a certain minimum. You can't go down to nothing. And if your system doesn't require that flow, then you need a bypass. And also you need to check the minimum chilled water loop volume and determine whether a buffer tank is required. What I propose to do in a later stage is talk about chillers in more detail, and all these things will come in. But the minimum loop volume is the volume of pipework or volume of water in the chiller circuit before you get to a bypass valve. And each chiller manufacturer has a minimum requirement for that. If you can't achieve that with the layout, you have to put in buffer tanks, which are basically just a big tank, a big pipe, if you like, which has a volume, which added to the water volume, added to the pipework volume, satisfies the chiller manufacturer's requirement for the minimum loop. So just watch out for that. I won't go into any more detail now because it's a topic that we could spend a bit of time on. Of course, chemical treatment of the chilled water is required. It's a closed system in this case. Now, condenser fans and compressors can cause noise issues. Sound attenuators may be required for the fan discharge and possibly the air intake. So be aware of the location and surroundings. Over the years, air-cooled chillers have got quieter, the compressors are quieter, the fans are quieter. They're developing all the time and getting better, but they still may be a noise problem. Sometimes an architect or builder may want to hide the chillers on the roof or outside. If it's on the ground, they might want to put them in an enclosure so you can't see them. That's all well and good, provided there's enough space around the chiller for it to function properly. Okay, you've got to get air in and air out. So going back to the chiller again, you've got to have clear space for the air to come into the condenser and clear space for it to discharge. If they want to build a wall around the chiller, you can do it, but you need certain clearances, and the clearances may or may not be in the chiller manufacturer's technical literature. If they're not, you need to talk to the suppliers and tell them what the architect wants to do, and and get their advice on what clearances you need. Generally speaking, you wouldn't want the walls to go any higher than the top of the condenser fan. If you go up higher, then you start to get recirculation, where the air is, if you've got wind blowing over the top of the enclosure, that can cause downdrafts inside the enclosure, and the hot air is not getting away properly. And then the hot air starts to recirculate, so the air coming into the condenser is hot, and the chiller starts to derate, and so you're going to have problems with capacity. Individual air handling units and fan coil units can be controlled independently, and periodic maintenance is required for those, and filter access. Air handling units are normally installed in plant rooms, so access is normally quite good. Fan coil units above ceilings, as we've said before, you need access for the fan coil unit itself and filters. Now, in a chilled water system, the heating source is normally a hot water boiler. And we've talked about these in the last session. We have conventional boilers or condensing boilers. Conventional boiler, physical size will increase with increasing capacity. Typical hot water temperature range is 60 to 80 degrees Celsius. Water treatment is required. Again, it's a closed system. Natural gas, LPG or oil supply is required. You need a flue to take the, or if it's installed inside a plant room, you'll need a flue to take the exhaust gases outside. Beware of the material you use for the flue because of potential corrosion. So stainless steel is the preferred option for flues. Boilers can be internal or external. I'll just bring up that boiler again to remind you what it looks like. So that's a typical conventional hot water boiler with a flue connection at the end, big burner here. So again, access, ventilation for plant rooms. Okay, significant maintenance required. Again, here, heating water automatic bypass valve will probably be required in the hot water system. The length of pipe is virtually unlimited. Clear space required around the boiler for access and maintenance. And again, the air handling units can be controlled independently and so on. And then we look at a condensing hot water boiler. Considerations basically the same as the conventional boiler, but with the following exceptions. The typical hot water entering temperature must be below 54 degrees to enable heat recovery from the flue gas. Now, we talked about this last time. I'll show you the schematic again. So the water coming in has to be less than 54 degrees for this condensation process to occur, preferably lower than that, so that you get the maximum condensation. So this might be 45 to 50 degrees, say, coming back. But that's going to affect your coils as well. So if you're going into an existing system, you need to look at the coils to see if they can function properly, give you enough heating. You have a flue gas heat exchanger inside the boiler, which preheats the water coming back from the system and then goes into the burner section to heat it up to the supply temperature. You need an acid neutralizer in the drain because the condensate is acidic, and any condensate that occurs in the flue is acidic as well, and you will get condensation in the flue because as it goes up, it cools down. It's cool outside, so you'll get some corrosion occurring in the flue unless that's stainless steel. Higher energy efficiency due to the heat recovery process. You can have multiple gas burners and variable water flow. It's more expensive than a conventional boiler. The condensate produced is corrosive, as I said, so just be aware of that. So we're on to water-cooled chiller. So in this case, the chiller will be in a plant room, and it's going to be connected to cooling towers or fluid coolers, which will be probably on the roof of the building. So a water-cooled chiller must be installed in a weatherproof plant room. Some manufacturers these days can actually provide you a kit, like a flat pack plant room, if you like. So you can put a water-cooled chiller on a roof and build a plant room around it. Obviously that's expensive, but typically they're installed in a plant room. Plant room ventilation is required. Capacity can range up to 10,000 kilowatts per chiller, as I said before, and the length of that chiller would be around 7 metres. Okay, let's just get here. The required chiller capacity will inform the chiller options available. So it could be a screw compressor or centrifugal. Centrifugal, there's a few options there. Could be magnetic bearing centrifugal, could be an open drive centrifugal or a semi-hermetic centrifugal. The chiller we looked at previously, the water-cooled chiller, this is a semi-hermetic centrifugal compressor. And you can get them up to, with trained chillers, which go up to, or carrier, up to 10,000 kilowatts. You'd have 2 of these chillers and some semi-hermetic. With the York chillers, or Johnson, they used to use open drive. I'm not sure what they're using there, but pretty big motors to drive these compressors. And looking at this chiller, this is the condenser. You need access to the condenser for cleaning out the tubes, which should be done every 12 months. So there are all these nuts and bolts on the end here. But undo all that and take the end off so you can get access to the tubes. These end plates, because if you've got cooling towers in the system, it's an open system, these end plates are often made of steel, so they're subject to corrosion. So they want to check those every 12 months as well and see how they're going. Sometimes they'll have cathodic protection on these ends. They're called water boxes, okay? Water boxes is a common term. Or you might want to look at the materials of the water box and choose a different material which is has good corrosion protection, such as stainless steel. Obviously, they cost more, but you can get them. Also, the tube sheets inside can be different materials. The tube sheets support the tubes as they go through. You can get those in different materials as well. You can also get marine water boxes for condensers. They still have all these nuts and bolts around the perimeter, but they're on a hinge. So when you've undone all that, they just swing out of the way. This particular one on this photo here, when you've undone those nuts, you have to take that off and drop it on the floor. But if you've got a marine water box, it'll just swing out of the way, which is a lot easier for handling on site. But guess what? It's a lot more expensive. So you don't necessarily need a marine water box. And if it's specified, it's worth looking at whether you can do something else, because a marine water box might cost per chiller, might be another $5,000. They're quite expensive. Anyway, when we talk more about chillers, I'll go through that in more detail. There's so many things you can do with chillers and so many different options. So as you go through the different compressors, the energy efficiency will be different for each option. The most energy efficient will be the magnetic bearing centrifugals, typically. But when you get into the very big chillers, that's not an option anyway. So we'll go through that in more detail later. Just going down through the notes, consider how many capacity steps are required if there's no speed control. Normally, you will have a VSD on a large water-cooled chiller. Now, here's another thing. Just highlight that. Ensure that clearance is available for compressor removal, and hoisting facilities may be required. If you've got a large chiller with a centrifugal compressor, just going back to this one here, they seem to have pipes over the top of the compressor, which is not a good thing to do. If you've got to take that chiller out, you've got to be able to disconnect the pipes and then lift it up and then out to get it out for service. It looks like in this diagram that may not be possible, but it's a bit hard to tell from that photo. But always be aware that you might need a lifting beam over the top of the compressor, or a monorail on the big compressors. A monorail is a good idea, where you can come in, lift up the compressor, bring it out, and drop it down to the floor. It's a major consideration. Oh, here we go. Sorry. Refrigerant pressure relief may be required. So if the chillers have bursting discs built into them, if they happen to burst because of overpressure, then you can't just discharge that refrigerant into the plant room. It's got to be taken outside. So just bear that in mind. I've mentioned over and again, clear space is required around the chiller for satisfactory operation and maintenance. Tube withdrawal space is required. Talked about that. Consider corrosion protection options for the condenser materials or cathodic protection. Consider the type of materials of water boxes to be used for chiller and condenser vessels. So I talked about it before. Marine water boxes may be specified for the condensers at additional cost. Some clients, we did a university job in Sydney a few years ago. They didn't want water boxes. They didn't want marine water boxes. It was actually in their own. The university had their own brief guidelines, and they had marine water boxes in their specification, but they actually didn't want them. So that was, by having that discussion with them, we were able to delete those, and it saved a lot of money, and they couldn't really see that they would get any benefit from having them. So that was good for them and good for us. And again, we've got the cooling towers. So space and access is required for cooling towers or fluid coolers for heat rejection, together with the pumps and all the rest of the gear. Significant maintenance is required. So with the water-cooled system, the energy efficiency improves. So on big systems, it'll always be a water-cooled chill water system. And the chemical treatment is needed for the condenser water system. So again, I've noted bypass may be required. It probably will be required, and make sure that you achieve the minimum leak volume. And again, boilers. In this system, you're going to have conventional boilers or condensing boilers. So it's a bit of a summary of what we've talked about in previous sessions, but in the next stage, which is not planned yet, but we've got some thoughts on what we're going to talk about. I'd like to go through the central plant in a lot more detail. There's a lot to talk about, and you're all getting to that stage now where you're working on projects, which have this sort of equipment, water systems, chillers, boilers, tanks and so on, and we need to start to focus on those and learn more about that. So we haven't got time now to talk about in detail anyway, but we will do in a later session. So managed to get through all that in time. Any questions?
I got a question.
No? Yep.
Do you have a picture of what a marine water box is? Is that like
Oh,
an add-on or?
Actually, I probably should have Googled one of those, but if you Google marine water box, I can do it now if you like.
Yeah.
I'll do it while we're talking. It's just a bit deeper than a standard water box, but it's got the hinge on it. So we'll see what. See if I can find some pictures. Marine water box. Images of marine water box. Can you see my screen?
Yeah.
See all images. Oh, here. Oh, there's one there actually. Okay. Oh, okay, can you see that?
Yep.
Okay, so that's basically what it looks like. It looks the same, but it's just got the hinge on the end, so it makes it easier to because they're very heavy. You know, these on a big chiller, those boxes are usually made of steel or stainless steel, so they're very heavy. So you need some sort of lifting device or two very strong men to lift it off. But if it's got a hinge, you just swing it out of the way. And you can see the tubes inside there. Can you see those tubes there on the tube plate or tube sheet?
Yeah.
And up the top as well. It's a bit dark, but so they've got to clean them out, and they use a rod to push through all those tubes and get the muck out of the tubes that's collected over time from the condenser water system. If you have a cooling tower, it's essential to do that every 12 months. If you've got fluid coolers, which is probably unlikely, but if you did have fluid coolers, you wouldn't have the same issues because it's a closed system. Anything else? Any other questions?
All good for me.
Yes, thank you. All right. Well, as I said, it's a bit of a summary of what we've been talking about. There is a lot more detail that we will go through later on. And if you've got any questions or suggestions for things that you'd like me to cover for you, just send them through. And because we're always working on things that are relevant for you guys, that's the whole purpose of it, to try and introduce you to these things and gradually work into more detail. There's not a lot of value in giving you a huge amount of detail on things that you're not dealing with at this stage. But as you get into more complex projects, we need to give you some help with what to expect and how to deal with various situations. But I think the time is good now to talk about chilled water systems in more detail and hot water systems, because we're getting more and more into that. And then that's also going to lead into control systems, BMS systems and DDC systems, to control all these bits of equipment. So it just we're just building up the systems, I suppose. We've looked at the basics. Air-cooled systems are fairly straightforward. VRF systems have more complexities. Chilled water systems have even more complexities, but interesting projects, and you'll be doing that as you progress in your careers. So if you've got any specific things you'd like me to cover, let me know, and we'll work it in for later sessions. All right. If there's no other
Thanks.
questions, I'll let you get back to work, and we'll see you next week. We don't have a session. Sorry about last week. I was getting myself confused there, but we don't have a session next week because I've got a wedding coming up on the weekend, so I've got a bit to do there, and so it'll be the week after. It's 2 weeks from today, I think, is the next session, but I'll send it all out. I'm going to be away for a week. I can send out the notes. The notes are ready to go. I can send them out today if you like, so that you can have a look at them in your leisure before the next session 2 weeks away. Or I can send it next Thursday. Probably next Thursday would be better, wouldn't it? Because you'll get 100 emails by then, or maybe 500. So I'll leave it until next Thursday and send them out then. All right. Thanks for your attendance. We'll see you soon.
Thanks, Bill.
Thanks, Peter.
See
Thanks,
ya.
guys.
Okay.
Take care.